So this video is more probability, and we're looking at the addition and multiplication rule, or you could think of this as or and. So when we're reading through the problems, addition is like or. So the probability of this or this is more, right? So we're going to add them together. If it's this and this, that's a harder probability. So the probability of getting an A on my stats test and getting an A on my, English test. What is that probability? That's a harder thing. So it's a timesing. So those are the rules we're kind of looking at. So let's look at the addition rule first, which we know goes with or. And the way that this is set up is it you can sometimes just look through this part, and that is just to add one and the other. But you have to be careful that this part might need to be subtracted. So what is that? Well, it's the probability of this and this, or excuse me, or this, but the and has to be subtracted where they both are. You don't want to count it twice. So I'm going to scroll real quick to a chart just to kind of go over this. If I'm looking at the probability of an order being accurate and from A, if I added all these accurate and I added all these from A, I would have counted this number twice. That number is the and. Where are they both? Well, they are both in restaurant A and accurate at 332 people. Okay, so and is where they are both, and or is obviously two separate things. So this part comes into play just in case you have overlap. On a Venn diagram, also, you might see overlap, that middle section that's in both. So remember, like a Venn diagram, right? So it's like maybe you have A and B, something like this. This colored part that I'm going to shade in, that's the and. So if you're looking for this and this, you have to be careful not to add the middle twice. Okay, so don't know if that's much helpful, but that's where we're going with that one. We'll do a couple problems. Disjoint sets are sets that have nothing in common. Okay, they could be called mutually exclusive as well. So they have no other lap. They cannot happen at the same time. No overlap. One is not affecting the other. So where you see some disjoint or sets that are affecting each other is like if I'm reaching in and I'm taking out a ball for bingo and I leave it out, well, that's not going to happen again because I took it out. So it affects what's left in the bingo game. Okay, so disjoint sets. They also could be activities like, like we looked at restaurant A and inaccurate order, those have stuff in common. So, well, yeah, I can't think of another example. We'll just go on. So disjoint sets, and then there's just a little summary. Let's look at an example. So we'll actually use this table. So the first thing you want to do when you see a table is if it's not given to you is to add up all the numbers, because when I do a probability, I have to have the total number of people in the survey. So the total number of people is adding those all up. I got 1,133 total people. Okay, now let's look at problem A. If one order is selected, find the probability of getting an order from restaurant A or, so this part's important, an order that is accurate. So I'm going to highlight all of those. So we have accurate and restaurant A, right? So all those highlighted areas are what we want to add up. So we just don't want to add 332 twice. So we're going to add those all up. So our probability of this event, I don't know if I feel like writing out from restaurant A and accurate, is going to be the 332, the 278, the 239, the 147, and the 38. Oops. All over 1133. So I just got to calculate that out. So I'm going to get 332 plus 278 plus 239 plus 147 plus 38 is 134 over 1133. So your answer could be the reduced version of the fraction. It could be, which is a lot of them, or it could be the decimal, so I'd actually have to divide, or it could be the percent. So this one is about 0.913, so about 91.3%. Okay, part B. If one order is selected, find the probability of getting an order that's not accurate or is from restaurant C. I'm going to erase our highlighted because now we're moving on to a different one. So we want not accurate this time and restaurant C. So we'll add those all up. I don't know if I'll write it all out, but I'm gonna add it up. 239 plus 38 plus 50 plus 34 plus 15. I got 376, and I did not count that 34 twice, right? This number here, that is in both C and not accurate. I only added it the one time. Okay, so divide that by the total, and the probability is about 33, round that to a 2, 33.2 or 0.332, or the fraction answer. Last one, if one order is selected, find the probability of getting food that's not from restaurant A. Well, goodness, it's easier just to add the restaurant A's numbers and subtract from the total than it's going to be to add up all the other 6 numbers. So I'm going to take 332 and add 38. So this is in A, right, is 300. That's a great 3. 370. So not in A is going to be 1133 minus 370, 763. So the probability of not A, right? There's our symbol for not A, is going to be the 363 out of the 1133. And you could divide it and do all those things if so needed. Okay, so you can use that idea of not. It's super helpful. Next question. Use the following results from a test for marijuana, which provides a certain drug company among the 132 subjects with positive test results. There are 32 false results. Among the 168 total negative results, there are 8 false negative results. If one of the test subjects is randomly selected, find the probability the subject tested negative or they did not use marijuana. So we want to know everyone that didn't use, right? So if you tested negative, oh wait, well, we still have some naughty ones in there that got away with it, but we'll, right, tested negative and did not use marijuana or did not use. So we want no one to have used it. That's how we're going to think of it. So let's think this through. First of all, how many total people are in the survey? Well, they say among the 132, 32 of those. So the total in that category is 132, and the total in the next one's 168. So the denominator is going to be 300. Okay. You have to read it carefully because you could have to add the 32 and the 8 in there. It just depends on how they worded it. So then we want to know how many people tested negative that were actually did not use. Let's do that. Tested negative but did not use. So negative and did not use. So for this one, we have negative test results was 168, but we have to subtract off 8 of them to get 160 because 8 people got away with a false negative result. They actually smoked some, I almost called it ganja. I don't know. some dope. No, I think dope's, I've never done any drugs in my entire life. So I'm not a good one with the names. I was going to try to be funny. I'm just really not that funny. Okay, so then the next category would be the probability. Oh, I shouldn't have the probability. This is just the number. Sorry, because it is just how many are in that group. We're just adding them up. And then how many are in, they tested positive, but they didn't really use positive. Oh, let's just call that a false positive. That's going to be 20, nope, 32. So 32 people tested positive, but they didn't actually use. So that's our total. We have the 160 and the 32. So the probability for people that were negative or didn't use is going to be the 160 plus the 32 over the total. 160 plus the 32. So 160 plus 32 is 192 out of the 300. So I got 64%. Now, I mean, this could have been read as just people who tested negative and who didn't use. I read it as they didn't use it at all. So be careful how they word that. It could slight change, right? And it changes what they're asking for. All right, let's look at complementary events. So we've looked at this idea already a little, and we've used it just a second ago, kind of. But you know, all probabilities add to one if you have the entire idea in one thing. I'm not getting that out very well. So basically, you have the probability of rain or no rain. Those add to one. So that because those are the only options that I'm thinking of right now. It could be rolling a dice, 1, 2, 3, 4, 5, 6. All of those probabilities add to one. Could be flipping a coin, one half, they add to one. So all the events in some, all of the possibilities in an event all have to add to one for probabilities. I still didn't say that very good. All probabilities in an event have to add to one. So we use that a lot. And again, the line on top just means not. So look at problem 3. Problem 3 says, based on a journal article, the probability of a randomly selecting someone who has sleepwalked is like 0.92. Okay, based on blah, 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 blah. If a person is randomly selected, find the probability that they didn't sleepwalk. Well, we know the probabilities add to 1. So I can take the probability of not sleepwalking, right, is going to be 1 minus the probability of sleepwalking. So we're just going to subtract those two. And what is that? It's about 70. 1 minus 0.22 is not 70, but 0.708 or 70.8%. Okie dokie. So we can use that not in kind of a lot of places, and they get a little tricky with those ones in the next section. So if the probability of no snow today, what's the probability of it actually snowing? I didn't even use the 25. What's the probability of no snow is 25%. So then no snow would be 75%. So 100% is 1. So it can add to 100% because that's the same as the number 1. Or you can think of it as 0.25 plus 0.75 equals 1. So let's move on to the multiplication rule. If you have two events and you want to have them both, you multiply your results. So and multiplication go together. Let's worry about this in the next section. Okay, independent events are, so I said disjoint sets were like this too. They're very similar. So disjoint sets have nothing in common. Okay. Independent and dependent are where like the second probability is dependent on what happens to the first probability. So if I reach in and grab out a bingo ball, it's going to affect the next one. So those are dependent events unless I replace it. If I keep them all in there, take it out, look at it, put it back, and then those are independent events. So independent and dependent are just where one affects the other. Deck of cards, if I'm handing out cards, if I've handed out 30 cards, then I only have, 22 cards left in my hand, and those affected what's left. So they're dependent on each other. Um, and disjoint don't have to be necessarily something coming out. They can just be two things that have nothing to do with each other. So disjoint sets just could be like how well you do on your test versus how large your head is, right? There's no there's no correlation between your head being big and a bigger brain. Well, your brain's circumference might be bigger, but it doesn't mean you're smarter. Yes, maybe. There really is no correlation though. So let's look at a couple problems. So this one says positive test results were 45, negative were 5. So there's a total of 50. I don't know why they had to give me a total. I'm pretty sure I could have got that. So if 2 of these 50 subjects are randomly selected with replacement, find the probability the first selected person had a positive test result and the second person had a negative test result. So, and we're going to times these two. So the positive test result could be, we could do it this way. A probability of a positive one is going to be the 45 out of 50. Okay. Probability of a negative one was the 5 out of 50. And those were just given from looking at our data up here. So we would just times those for the probability of the and of a positive and the second one being negative. Okay, so that's going to be 45 over 50 times 5 over 50. So we times straight across, reduce, divide it, put it in your calculator. I got about 0.09. And you have a fraction key in the math section. Use division, then click that math fraction key. It's the first one. It can reduce your fraction for you. When they get really big and you struggle, it's fine. Just use the calculator. And that's just on the graphing one. If you have a different one, you'll have to Google it. Okay, so repeat part A, but let's assume this time that without replacement. So now we're going to keep that out kind of idea. So the first one is still 45 out of 50. But I'm going to leave that person's paperwork, whatever, their name out of the hat. And I got to times it by negative. Well, how many people are there still in there if we took one of the 45 that are negative? There's still all 5 people. If I would have said positive, that would have been 44. I would have had to count down. Now I still have to count down to the denominator. So sometimes you count down on the numerator and the denominator. Depends on the question. This one was only the denominator because they were very different things. So if I times those together, I got 0.09, oops, I forgot the 0, 0.092-ish. So very close, but not the same for keeping them in versus taking them out. So independent versus dependent. Which one of these, A or B, is dependent? B. The second one is dependent on what you got for the first one. So dependent. I pointed. All right, we talk a little bit about sampling. I've already said this, you're independent if you with replacement without your dependent, so those are there. We have this rule of like 5% cumbersome rule. It's like we can just treat things as independent, even if they're not, if we're talking of such a low number. So this first example I'll give that, but it's like less than 5% overall. So an example of this is problem 5. Assume that 3 adults are randomly selected without replacement from 247 million, blah, 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 that big, massive amount of people in the US. So assume that 10% of the adults in this, so literally 3 people are being chosen from that. That's a super small amount. the probability is 10%. That doesn't have to do with the 3 that we're choosing from that. So that our sample is 3 out of that. So 10% is bigger than 5%. But this is still going to be we're just going to treat it like dependent, even though it's not. And so the way that we're going to do this one is we're going to just take the 10%, and that's our probability for that first person. Okay. And then we're going to times it by that second one, same probability. Maybe if I put a 0 in front, that may not look terrible. And then we're going to times it by the 10% again, because it's 10% for every single person. There are other ways to do this. You could find 10% of that massive number and then write out the fraction of that 3 times, where you count down on the top and the bottom. You'll actually get the same answers the way I'm doing it. And it kind of just depends on how you think through some of these. So the example button is not always helpful, and the way I do it is not always helpful. You have to think through like how you are interpreting these. Now you can't get the wrong answer, but all of us can be doing a little bit different and still get the right answer. Okay, so we times all 3 options together and got the 0.001. I didn't want to do it the other way because I want to treat it as independent. All right, next one, last one's a little bit tricky too. This one says that we will assume for a typical flight, the probability of a hydraulic system failure is 0.002. If Airbus 310, that's just the name, 310 is not part of the problem, were to have one hydraulic system, what's the probability the flight control would work? So probability of failure is 0.002. We only have one of these. So we could just take 1 and minus this 0.002, and that's going to give us our probability of the 0.998. Okay, so part B, given the Airbus 310 actually has 3 independent, they don't have anything to do with each other, systems, what's the probability that on a typical flight control can maintain with a working hydraulic system? What is the probability? That's worded a little bit bad, but like, I stole this from the book, so I don't know. It's trying to get you to think of each one's independent. They aren't affecting each other. And if one fails, you're still alive, right? Versus 2. So you cannot use the 0.98 times itself 3 times, because that's like saying all of them fail, I die kind of idea. Whereas the 0.02 is per each one. So we're going to think of this as 0.002 times 0.002 times 0.002. And this is the probability of failure. So probability with 3 of them, 3 fail or less. Okay, so I'm going to take 0.02 to the 3rd power. Oops, I'm missing a 0.002 to the 3rd power. What it gives me on my calculator is this, okay? That's a little tricky. That's scientific notation. You have the number 8, so you have a decimal right here for 8. And if I move that decimal in the left, because it's negative, 9 times, that's 1, and then I would have 8 more zeros. So this is the same thing as 1, 2, 3, 4, 5, 6, 7, 8, and then the number 8. I almost put the number 9. 8. So 9 moves. So that's our probability of failure. So our probability of not failing, of no failure, then would be the 1 minus the 1, 2, 3, 4, 5, 6, 8, which is going to be 1, 2, 3, 4, 5, 6, 7, 2. All right, my numbers got a little sloppier. So I had to use the failure and subtract it. If I did 0.998 to the 3rd power, It's not gonna be quite the same answer. Similar, but it's not because that's like saying, um, that you have, wow, this it's like saying all 3 fail at the same time. That's how I want you to think of that one, I guess. This is 1 or 2 or 3 fail, right? That's this probability because you can still go on 1. You're not gonna die yet. Okay, all 3 have to fail for failure. All right, those are tricky. So a lot of your homework is going to be from a chart where you're doing an or from a chart. So remember, or is going to be adding up all the different ones that meet your categories, like we did with these highlighted ones, and is where they're both at. So it's like a certain spot. That's our and. Okay. And so you'll be doing quite a few from a chart, and you'll have a couple that are going to be a little tricky. Do the best you can. Please use the Ask the Instructor and send them to me if you need additional help.